some data from my work, and it's local data on our spatial area of responsibility on landfills and abandoned industrial places, abandoned military places. We collect them for the state, and it's just, of course, it's in Germany. Yeah? So just for explanation, we take care about dump sites, abandoned industrial complexes, abandoned military complexes, and other types of hazardous situations for soil and groundwater. For example, a car crash on the Autobahn. Yeah? There's oil dripping, and we try to. There is a database in the build-up phase, and since not so long time, we start to collect coordinates for the events. So, of course, for events like the crash on the Autobahn, there is exactly one coordinate. But if you want to have a look at an old military base or so, it's spatially distributed around hundreds of meters, kilometers sometimes. So one single pair of coordinates is not quite the best way to represent it, but at least we have it some for this time. So, and I recognized during my work within the last year I started there that if you compare the sites where you find these places, especially old dump sites that are not known anymore, or sometimes they are covered now by grass, and nobody knows it anymore because the generation who put up their dump and trash there, they are not there anymore. So it's forgotten. So when we find them, I recognize that sometimes geological mapping has gone over it. So geological mappers sometimes recognize that it is some kind of technical landfilling, or sometimes that they find within these sediments or the upper layers of the soil sometimes products of industrial enrichment of minerals, for example, coal or heavy metals or something like this. And therefore, I tried, hey, how would it be if I can get geological mapping data and try using machine learning to find out where I can expect unknown places based on geological mapping, but not known in our database up to now. So therefore, I tried to run geological mapping classification to find where I expect the one that I know, and further to predict where I can find similar geological situations where maybe the rate is high to find such old dumping sites or landfills. Can you get it in a way? Yeah. Okay. So so I brought something. Should I expand it? It seems to be a little bit small, huh? Really? Yeah. Because I can't read it, so no, it's not. I basically know what is. So you can do that. So, but I don't know how it is in your country with geological maps. In Germany, they are digitalized, but they are still, you get it still in sheets, tile per tile, like in a raster, yeah? Especially the higher resolution ones. And because it's some kind of a historical developing behind this data, and geologists are dying out, it can be that one tile is a map that is 10 years old because geological mapping has gone over it. And the one besides it, the next one, is 120 years old. So because nobody has remapped this area. So, and in Germany, it's really a problem. Of course, in other countries, it would be the same problem because for 120 years, they do not know about tectonics. So it's a whole complete school of geology. So these type of geological maps I brought with me cover the area, but they are not unified in their information. So because it is not done yet by German geologists. So it's quite a annoying thing to work with this type of data because you cannot say, it can be say, on the one tile, it's limestone, on the other tile, yeah, they didn't know about the dinosaurs. Yes. Yeah, so it's because they had a different type of geological thinking. So you can imagine that it's hard to compare information directly, even if the tiles are spatially lying next to each other. So if you try to get information from these types of geological maps, you every tile can bring you a complete different set of factors because the groups, they are divided, they are dividing the the geological situation in their sheet can be completely different name than the last one or that the neighboring one. So you can think of that every tile you add, raise the number of factors you have. And especially in R, that's a problem if you try to want to do machine learning, because if you raise the number of factors, you finally run into some performance problems of R. So therefore, I will pick it up later. But before, I try to merge, and on Monday and Tuesday I merged the geological layers at the beginning by hand because I want to follow it. Then I saw that I made a mistake by merging it them with QGIS, and I asked Giuseppe a little bit in a panic mode, and he brought the idea with OGR, using OGR, yeah. And the problem with merging the maps together was done in a few seconds, just within a short code in Bash. And it still reminds me how powerful Bash is.
Yeah, this one you find very easily in the internet. This actually uses really the same name, consolidated.
Yeah. Okay. And it's a nice short script. It's based on UID and some idea from Stack Overflow. Yeah, it's an easy thing because it runs through all shapefiles in a subdirectory and adds them one by one, updating the one it generates at the beginning of the loop. So you can run it an infinite amount of shapefiles and subdirectories. And in my case, it was 70 subdirectories and 400 shapefiles. So the script does it in 400 in a few seconds. So
because this one was built before the OGR merge. Now there is also the OGR merge. They did the same, but we tried yesterday. There was some error.
Yeah.
So probably with this one you avoid also that.
Yeah. So it actually worked with this one because I couldn't find out the problem with OGR merge. So yeah. So after the script, I had some merged geological map of Germany. Or of my area, and you still see the single tiles. It's not really relevant, but just that you recognize that they are stitched. It's just a moment, and yeah, you see in some situations the structures are connected, but in some others they are not connected because maybe these geologists describe the same geological situation completely different than this one. So yeah, 100 years of scientific history in between. So yeah. This is the information from geological maps, and then I'll add all the dump sites and old industrial abandoned places thing about 14K of these events, and I factorize them by if it is an old dump site, an old military site, or an old industrial complex, and just colored them after they are this type of use. And I loaded the data into R. Because I still like R, and I crashed my Python environment on
several times.
several times installing Conda. And therefore, I remind me to what I use in my master thesis, because I run into these performance problems of R using lots of factors. And I found these H2O library. And H2O, I think it is an interesting environment, especially for us, because it's a machine learning environment, and you can communicate with this machine learning environment either from R or from Python. So it fits perfect into this course. So, and because I crashed my Python, so I used R and used H2O, and started to initialize the package. And I will explain something about H2O during the next lines, because if you start H2O runs in the background and it generates a whole environment. Here you can see that it uses 1 GB of my RAM, and it uses 4 cores because I'm running it in a virtual machine, the whole thing. So if you run it on a cluster, it uses all the cores and all the RAM you are giving it to him. And H2O does something like the whole machine learning environment of H2O is written in a special Java code, and they are using a high performance storage management system, so they can handle much bigger amounts of data than the other environments. And therefore, I can use it with all these factorized data that I used using geological maps of whole Germany, for example, in my master thesis 2 years ago. I found that it is relatively powerful, comparable to the other machine learning modules within R. Where's my mouse? Oh, yeah, there. Yeah, it's just the regular thing you read in your code, that your data code, and you see all the factors of my data variable. So some kind of ID for these dump sites, and behind these art of the area, there is behind, if it is a dump site or military site, or any else. For me, this is my target variable. This is my variable. I want to do my classification to find out, can I predict these type of variable with its 5 factors. So
and the 5 factor is down to military side.
Yeah. And coordinates, addresses, and here behind this block, there is the geological geological map data, because every geological layer from a geological point of view is labeled by special geological IDs of generation, because you can have the same, you can have limestone, for example, from different ages. Behind these ideas, this information is hidden, and you see that it is a bigger amount of factors in some situations. And it is automatically detected as integer. Yeah. So I just run a summary on it. I think we don't have to look at it now. It's just, where is the information? Yeah, there you see it's an old dump site, an old industry complex, one of these other types, and these other types of landfill and dump situations or damages, and the amount of them. So yeah, let's go through it. And just in R, just have a look at the spatial extent. So it seems familiar with these dots to the upper ones, just a short plot. Yeah, so I think you can have an idea what this does. So I'm feeding my data with the columns of interest, because I don't want to fit the whole data. I feed the whole data to my HTO environment. So it's the point where it is leaving R, and it is loaded into the back frame and of HTO in the background, and then I use from R the HTO commands and work with my data in HTO, split it up, the classical 80-20 split for training and testing. Here I declare my target variable, and which variables, in this case I choose all the rest to explain these. Oh. Yeah. Oh. Mouse is hanging. And here I explain H2O that it should use these stuff as factors, because the ideas of the geological maps are labels and they have no numerical background. So 4 is not the double of 2. 4 is just something else than 2. And nice. Okay. No. Then I don't know. We have heard a lot about machine learning, but in my situation, sometimes it's the problem. Okay, I know something about neural networks. I know about gradient boosting or distributed random forests, but I have a type of data and I don't know where to start. I just know, okay, I want to do a classification problem. So nice thing of H2O is I can use an auto machine learning model, feeding it with my data and letting it compare, letting H2O run just some samples on it and try to answer my question, which machine learning module can handle my data. So I think if you can read the code, it's just a simple thing, yeah. The variables telling which is the training data set, and just make some limitations that the time doesn't took too long to run, and just say, okay, save it as my auto model, and let's have a look which method suits to my data. Because I just want to use a classification. For me, it's not necessary if not now, which type of method I should use. Okay, it took a while. And
but for example, if you want to know which method we use, is there a way to know?
So you know.
Yep. So in general, it compares GLM. So what is this? General linear modeling,
Yeah.
GBM, gradient boosting machines, DRF. So distributed random forests, XGBoost, neuronal networks, and it also does stack assemble.
But for example, for this prediction that you're doing right now, right? Do you know which model was used or all of them?
All of them.
All of them?
Yeah.
Okay. So if you want to use this trained model, you just call for this auto ML now and you run the prediction.
Yeah.
Yeah, they do also.
But in a very, and because it's a machine learning environment, let the environment make the basic surroundings. I just feed the variables and say, do it, play with it. Yeah, I know it's, but
we need this kind of stuff.
Yeah.
What are we doing here? Let's just use that for now.
Yeah. Yeah, because you see, it's really easy. Yeah, I just say play with it. Yeah, I don't make any restrictions. Yeah, just say okay, go not too deep or not too long. Yeah.
You only train each model for 60 seconds. That's it.
Yeah.
Oh.
Okay, in fact, it took half an hour in my PC, but yeah, there are some things going on that are behind, far beyond this. But yeah, and it gives me in the variable in return, it gives me a leaderboard. So we can have a look at it. Which type of models lead the predictions or my task that I have given it? And then from the definition, it was classification thing. Yeah, and now we can go in a classical R view and R style through tables of variables that measure the quality of the outcome. And we can see, yeah, XGBoost seems to be the leader, then distributed random forests and the stacked assemble models. Class error, yeah. So bigger error, better, later, yeah. Worse performance, better performance because lower error. So XGBoost seems to do a good job. Distributed random forests too, gradient boosting and general linear models seem to perform not as good as the rest. And if you build stacks of these assembles, it doesn't make it better than the single prediction of XGBoost when you compare it with on these parameters.
Different type of metric. So
yeah, you can. I just use it as it comes. Yeah, and of course for it depends on the purpose you wanna look for. Yeah. So my last model, for example, that I ran for my master thesis, I used for this model prediction error.
But I mean, for example, can you use accuracy to choose your best model instead of least square error? Because it's hard to say like how good your model is doing in terms of age.
Let's answer this question later, because now we are in this auto mode.
Okay.
So of course you can directly use a method. So you can, for example, say, let's do distributed random forest, and there you can specify much more elements. We can also have a look to which parameters you can feed the AutoML mode with.
I'm sure that now we are running in a categorical classification mode, At least, yes.
Yeah, I'm sure because I you will see at the end because I made a mistake and
and for example, how do you put it in square aim or with that texture? You see that's like the you have me per class aimer,
yeah.
which is weird, but I was set. But the log loss, okay, fine. Root means square aimer for classes that I don't even know how you put this.
Yeah, I know what you mean. Yeah, yeah. And I don't want to, if you look at the values, I don't want to give much on it. But it also, I disabled the warnings, I think. So it so I knew, for example, in a former run, it threw some values out because there were missing errors. And for example, XG boost doesn't like missing values. Yeah, so it is for an overview. So in my perspective, and I just used it for which type of into which type of model should I dive in. Therefore, for this purpose, I use this AutoML function. You can enrich it with features. It is possible.
Maybe the larvaling of the color or something else.
I mean,
they are all of them below 0, below 1. So maybe they can be probably in that.
Maybe because it's just like browsing over several methods. The easiest one to like apply for all the methods at the same time is your regression. Maybe like by default it does a regression, auto
Yeah. Yeah.
Okay,
so that
check later. Okay.
Yeah.
Keep
Yeah.
going.
Yeah, and then we can just have a deeper look at the leading model, yeah, and make it in a classical R style, plot summary, and then we first see the classical summary stuff where we see how it classified, where we see the errors, and yeah, we can pass over it, and the 5 best hits. Okay. It's a little bit. Yeah, and then the plotting. Yeah, yeah, it's the classical R stuff, but we are using H2O, so we can also use, for example, H2O plotting functions. For example, plotting a heat map of the correlation of the model. So we just can see that the different models, of course, the correlation with the model itself is 1. And so because they are not completely correlating, I would say the models in detail perform different. And for example, what we saw at the beginning, XG boost does, for example, a good job, but with GLM, it seems to correlate less than with the others. And yeah, just to show the function, I don't want to over, how do you say, interpret this. It will be interesting later for other decisions. But H2O comes with another nice thing, because we can use H2O to help us explain what we saw and what we modeled. And therefore, I used the H2O explain function on the leader, so on XGBoost, feeding the test data into it, and having a look at maximum 5 features. And at the beginning, there's the code. And then it starts to feed us with pictures that help us to explain our data. And for example, we see that the variable importance of one of these geological data factors seem to be highly important to predict our or to classify our output value. So I see if somebody recognize. Of course, the areas seem not to have an influence, and the object ID, of course, not. But the other parameters of geological maps seem to have an influence to my classification, and it also gives us these functions where we can see how one variable of my predicted outcomes is influenced by the scale of mean response of these value that is leading the variable importance. So we see the range of the factors of the values of the geological factor, and see that it is, I would say, that the values and the response and the error drops around 3,800, for example. Yeah. So we have to dive into these variables if we deeply want to understand what it does. But I'm doing this now for an overview because did somebody think about why there is an variable importance of 1? Yeah, we can go through the other values for the classification, and we all get these generated by this explain function. So I formally use days to just make one of these things on my own. So it really helped me to do this, and we can use this explain function also not just on these automated machine learning things. We can use it, of course, on our final models also. So we will go down and scroll through it, and yeah, also see the influence of the values. So yeah, we can deeply dive into that, but that's not why I'm here now. We cannot just let the whole data set be explained. We can decide even for one row of our data set, especially if we want to find out if one single row has a special effect. In my case, it will be a special place. If we want to follow if the military area of one place, how it performs into the model. And then I can enter the row of this situation and have a look at all these diagrams just for this row within my data set. It's not. Oh, yeah.
How many blocks do you need there?
Yeah. I just it's automated.
It's automated.
Yeah, of course. Yeah. So I use one command to generate all these plots. So yeah, and then I can decide which one I want to take or I really need or not. Yeah. But else it is days to make just one of these plots sometimes. Yeah. So I really liked it, and because you can use the same method to different models. For example, yeah, you got some kind of like a standard to compare things. Okay. So yeah, you know what I mean? Yeah. These way of doing things, not the auto ML model, but just how I used machine learning on this type of geological data, brings some problem because we use factors. And if you see it, if you have seen it in the upper pictures, it arranges the factors by their size of the integer number. But as we talked before, 4 doesn't mean anything else than it is not 2. It is not bigger than 2 or something like this. So it's just a label and an idea. So I had to rerun, in my opinion, these functions and these machine learning stuff. And therefore I had to reconfigure my matrix, because in my opinion, and that is what I understand from machine learning so far, it would be better to use in R, and even if you tell R that this is factors, that for every permutation I have within my factors, to start a new field in my data set that is of a binary value, so 0, 0 or 1, and for example on limestone, yeah, just this is the column for limestone, and then go through all the data and see if it is limestone or not. And so to organize my whole data set to get at the end a table or matrix with all the cases, in my situation, all the places where these dump sites and areas are, 14K, with every value and every permutation having a column with a binary value 0 or 1, to really make sure that it is handled like I want to do it. Do you understand what I want to say? Because I'm not sure that it really gets my variables as a factor. Right. Okay. Because like it is now, yeah, it's like, yeah, for example, the landfill, for example, has the ID in the geological map of 284, and the pile or pile sediments can have 294, so, or time 290 or so, yeah. So, but it's just a label. It doesn't have to mean that it is bigger or lower or anything else. Right. So I'm not sure if giving it handling it as a factor variable, yeah, does really eliminate these possible misunderstanding that, for example, could happen. So in my master thesis, I really did this. I really split up the geological map into all of these units. I think at the end it was 50,000 values side by side for every case.
You can just like get to the conclusion, so it can go
yeah. The point is, I want to rerun it with better code and with this adapted string, and maybe add something in the future, because I'm just late now. and add maybe possibly to every dump site and situation the dryness, some dryness index for soil moisture, because if you look especially at dump sites, they are covered by clay soils to avoid that precipitation enters the filling of the dump site. But what happens during climate change, especially in lots of regions in Germany, that the soil moisture is decreasing after dry periods, and it's decreasing so deeply now that it reaches these clay coverings. They build up cracks, and for example, methane, CO2, and other gases can migrate, and precipitation can enter these dumps. And therefore, I want to try to add by a semi-automated algorithm, I don't know yet, these for every coordinate pair I have a prediction, and looking back of the SPEI of the last year's dataset flow used to store it in our official database for every dump site, that we can see, hey, could this dump site maybe be affected of these types of dryness or not? But this I will do in the next week. So just one thing. Let's go to the H2O stuff. Can you click on, because I didn't see the mouse. Yeah. Yeah. So I think if you want to use H2O, it's open source and it's well documented, I think. So we'll, yeah. Oh yeah. So let's just type in. Does it?
No.
Okay,
go.
Okay. For example, I want to just click on distributed random forest. For example, just because I think it's the one you are common with, a little bit about distributed random forests. Just for example, then an explanation of all the variables you can feed H2O with if you just want to make it to start a distributed random forest model, not an AML model. So I think it's really well documented. And at the end of every site, you will, yeah, and as you see, for R and Python. So the same explanation for both things. So I thought it is good to show it to you because it really fits well into this course. So yeah, I think if you search for H2O AI, you'll find it, and it's open source, so it's in the idea of our course.
Very good, Ron. First question for you: why your Python was crashing? Because some memory, or because it was some syntax error?
No, it was the memory management of R because of 50,000 factors.
So R was better.
No, it was that I was using R, and it seems to reach some finally of some for example, sometimes it was, if I try to use many of these R machine learning packages, yeah, but sometimes the memory reach bigger than 4 gigabytes, even under Linux. It seems to be a problem, or sometimes it just couldn't handle it, and with H2O I could use my data as it is.
Very good.
So
Somebody, another question? Last one? Okay, thanks again. Close the